Hello, everyone. So today we're going to be talking about what happens to phase diagrams when we start worrying about liquid-solid mixtures. And as you may notice, you may end up finding phase diagrams in more places than you'd expect. For example, they may be present in your ice cream. But one of the things we have to worry about when we go from, say, liquid to uh, solid phase diagrams is a tendency of liquids, by their very nature, want to be a mixture of multiple different components. Solids, however, tend to like to crystallize out as pure phases. And so what you'll find is uh, much more the case where you're going to have a species like species B here, which is just purely solid and has no A present, and similarly, a phase of A with no B present. And this is really going to essentially complicate our mixture because, for example, if I have a system of, say, of composition A5, its natural tendency is going to be to uh, solidify into two separate solids, one that's entirely B and one that's entirely A. However, things do get interesting as we reach higher temperatures, because what you may end up finding is a case, such as if I heat up my A5, what's going to happen is I have essentially generated, what I'm going to do is I'm still going to solidify to pure B, but I'm also going to generate an impure liquid. And this liquid's going to essentially be much richer in my A component. So essentially, one way to think about this is from the point of melting point depression. If I'm a pure solid, I'm going to have a fairly high melting point. But as I add in more and more B, this melting point is going to essentially depress. But interestingly enough, that when it does melt, it's going to mostly try and melt out the impure substance, the substance that doesn't want to be part of this otherwise pure solid B. And this is one of the things that tends to complicate these liquid solid phase diagrams. However, this also gives us an interesting tool to understanding this liquid solid behavior, and that's what's called the Liquidus line. So the Liquidus line is essentially going to be this line that gives us the melting point of our now impure solid. And not too surprisingly, it's going to be rather tightly controlled by the mole fraction of B present in the system. And we're also going to tend to see a very similar case with A, where if I take a system with a given composition, it goes ahead and I go ahead and heat it up. And what I'm going to find is I'll generate a liquid that in this case is going to be much more pure B, or much more rich in B, and generate a pure solid of A. And so what we're going to want to do is figure out how we can describe these liquidus lines. And it turns out that what we can do is we can generate an equation for these liquidus lines based on the mole fraction of the richer component. So if I, for example, want to describe the second liquidus line, I'll use the mole fraction of B, and not too surprisingly, its enthalpy of fusion. And then what I can do is essentially predict what the new temperature of melting is going to be based on my enthalpy of fusion, the normal melting point, and essentially how much I've contaminated the system. And again, at this point, we're assuming that the intermolecular forces of the two species are relatively similar, and you can actually deviate from these lines significantly due to non-ideality. But it's a good general sort of description for these behaviors. And we can use this to generate a set of equations. However, if I know the mole fraction of the species, and not that I'm trying to determine the mole fraction from an impure sample. I can also invert this equation, rearrange things, and generate what's called the Schroeder-Van Laar equation, where if I know the composition of a system, I can figure out how much I'm going to lower the melting point, again, based on what the melting point originally was, the mole fraction of the species, and the enthalpy of fusion of the dominant component. However, again, we can perform these same techniques for the other component by knowing its melting point and its enthalpy of fusion. And where these 2 points meet generates what's called our eutectic point. So in this case, this is going to be the situation at which I've lowered the melting point pretty much as low as it can go, which actually can be quite an important point to try and understand. For example, if I'm trying to, say, construct a good solder um, for welding, I might want to know essentially how low I can, I might want to generate a metal alloy that essentially has the lowest melting point it can. And then once it gets below a certain temp, it's going to solidify into the two components, which are going to be then fused together. And this is exactly what ends up happening with tin solder, as it's a combination of tin and lead at about 67 weight% tin. We also might want to know this for, say, sodium chloride in water if I want to know essentially how cold an ice bath can get, because I might want to keep my water as liquid as possible while still being as cold as possible. And so it turns out that you can actually get liquid water down fairly cold just by putting in about 23 weight% of sodium chloride, which generates its eutectic point. And this means that you can actually get liquid water all the way down to about negative 21 degrees C before it freezes. Again, entirely based on its phase diagram and trying to get as close to the eutectic point as possible. However, as soon as you reach the eutectic point, we're going to essentially completely solidify everything out by making our pure solid A and pure solid B. But again, one of the nice things is you can also predict the eutectic point for a well-behaved system simply by looking up the enthalpies of fusion of both components and their normal melting points, which are all widely available data, and then trying to set their temperatures, their melting temperatures equal to each other. And again, then solve for the mole fraction. And this is actually a very powerful tool in trying to control, to determine the phase diagram for a system, which then gives us a lot of control in figuring out the structure of a system at any composition or temperature. And again, a very powerful feature. However, one of the things we occasionally run into is the slight difficulty that not all solids are going to just form their pure species. You may end up with a lot of alloys, especially when mixed phases or alloys when working with metals. And a classic case is, say, something like gallium arsenide, which actually is a fairly useful species when you're talking about semiconductors, as gallium arsenide is a very popular semiconductor species and has some promise in the use of solar cells. However, it's also going to be generated by having a 50-50 composition of gallium and arsenic. And this means something rather interesting about what the phase diagram for gallium and arsenic is going to look like, because it means that I've got a possible third solid. So for example, let's treat, if I'm looking at this system of A and B with an alloy C, what I might have if I start with a mixed liquid of composition A and I start cooling it down, what's going to happen is that since my composition most closely resembles this alloy, when it starts to solidify, I'm not solidifying A or B, I'm solidifying this 50-50 mixture. And then as I go further down, I'm going to be continuing to make uh, more of the solid alloy, but I'm also going to be generating a liquid that is richer and richer in B until essentially I get to the point where I now have the same temperature as my eutectic point, at which point I'm generating not just my complex C, but also my solid B, as I'm able to go straight over, and the the two species that are on the right and the left are now my pure B and my alloy C. Now, again, when trying to generate an idea of how much of B and C would be generated, we can go back to our good old friend, the lever rule, which still works. As long as you know the lengths of the lines in between the two phases to the right and left of your isopleth, you're able to uh, correctly determine the amount of each of these complexes that are going to form. However, there's also some other interesting implications of when you have something like a alloy C in this case, or if we go back to the gallium arsenic fact, if I've got a complex or an alloy in the middle, it means that there's no way to form the gallium and the arsenic solids simultaneously. Because either I'm going to generate a liquid, but when I condense this liquid, it's going to do one of several things. Either I'm going to say make pure arsenic with a gallium-rich salt liquid. I'm going to make gallium arsenide with a gallium arsenic-rich liquid, or I'm going to make arsenic and gallium arsenide. Or over here, we can make gallium arsenide and a gallium-rich salt liquid. We can make gallium and a arsenic-rich liquid, or we can make gallium and gallium arsenic simultaneously. These are our only options. And again, it all depends exactly where we end up in the phase diagram. However, one of the things that is worth noting is that this is also still a fairly pretty unrealistic phase diagram, as in this case, we're making the assumption that we've got two eutectic points that occur at the exact same temperature. And this would be quite unusual. And while you may notice we do have slightly different melting points for our three pure solids, again, pure with respect to the alloy, the differences in the enthalpies of fusion do dictate that in this case, they've got all identical eutectic temperatures, which is going to be a very unrealistic case. And most of the time, we're going to end up finding something that's, well, let's call it a little bit more fun, like in the case of the sodium-potassium phase diagram. So again, this is for the pure metal species, not for the cationics. But in this case, if you have a mixture of sodium and potassium, well, a lot of interesting things happen. And I want to point out a couple of key ones. First, if we look over here on the right, what you're going to notice is that when sodium crystallizes, it's very unlikely that it's going to crystallize out as pure. And this region that you see here is going to be solid sodium with a little bit of potassium contamination. So some of that potassium is going to co-crystallize out with the sodium. And this is actually quite a common feature. Now, when we generate or show a straight line, especially when talking about solids, this is often a little bit of an over-exaggeration because there might be, even though it's very close, some amount of the other component always there, because it's very hard to have a truly pure crystal form. And we'll see the same thing over here with potassium crystallizing out with a little bit of sodium. And it's worth noting that as you go up in temperatures, this tends to essentially increase until essentially you get at the point where it's easier for it to eke out as a liquid because the other component it's easier to melt the other component. In addition, we also find the presence of a sodium-potassium uh, sodium-potassium complex. But one of the interesting things about this sodium-potassium complex is that it turns out that its melting point is significantly lower than that of sodium. And so what you end up with in this case is, let's say I have a composition of pure A, well, of A, as I essentially cool it down, I'm going to start by generating until I reach temperature 2. I'm going to end up generating some of my contaminated sodium and an increasingly potassium-rich liquid as I get cooler and cooler, until we reach this rather interesting point where I reach the melting point of the sodium potassium, at which point I no longer am generating the potassium-rich liquid. Instead, I'm generating the sodium potassium solid and my contaminated sodium solid. And this is going to continue as I cool it all the way down. However, if I just go a little bit more to the left, richer in sodium, we're going to see a slightly different case, where now my composition is slightly more potassium rich than my mixed solid. So as I cool it down, I'm going to again start generating my sodium, potassium contaminated sodium solid until I then cool it down enough that I go from generating my contaminated sodium solid to generating the alloy, and again, a potassium-rich liquid, until now I get to below the eutectic point. So I'm essentially so cold that I can't support the presence of any liquid anymore. At which point I'm now simultaneously generating a contaminated potassium solid and my alloy. And again, you can track a similar behavior if you go down any of these other isoplats. And so there's a lot of very interesting trends here. And again, I do want to emphasize that there is going to be a certain role of temperature in talking not just about the nature of the contaminated solids, but also in where these kind of interactions occur. But I do want to point out several trends in trying to figure out what you may be forming. And while these don't always hold, they're generally a pretty good rule. Whenever you tend to see solid straight lines on a phase diagram, this is often an indicator of a solid phase, being part of the system in some sense or another, simply because solids more often tend to have very restrictive compositions of what forms they can take, whereas liquids have a very mobile sort of structure. So whenever you see curved lines, they often mean some form of fluid phase is part of the system, whether it's a liquid or a gas. However, when you start seeing a region that's essentially bounded by a curved line and a solid line, as present here, here, and here, this is often indicating some form of being a two-phase region where you're generating a liquid and a solid. And again, while this rule doesn't always hold, it's a good kind of starting place to try and think about what may be present in these phase diagrams. So this brings us to the end of essentially systems with two components. Next time, we're going to dive a little bit into the deep end by looking at three component systems. Until then, take care.